I sometimes think about what you learn as an engineer or a scientist in early education that you wish everybody knew. And estimation, order of magnitude, going to limiting cases are really very useful things one uses again and again in ordinary life. Another is system boundary. And our speaker today is a person who's thinking very seriously about system boundaries and enlarging them so that the renewables world becomes part of a larger world in which can be actually a more productive innovation within the energy system. I've met Mark O'Malley only once before in a meeting last fall in Brussels. There was an aura about him. People were deferential. He had what I think is called charisma. I was intrigued. I wanted to bring him to Princeton so we could find out how he is affecting this field of renewable energy as a systems guy, thinking differently from many of the people in the field. Mark is a professor at the University College Dublin in electrical engineering. He runs two centers there, the Energy Institute and the Electricity Research Center. And he's a co-founder of the International Institute for Energy Systems Integration. He's a networker, he's a pioneer. Let's welcome Mark O'Malley.
Okay, so look, I don't know, they were very kind words, so I hope I can live up to them. So this is what I said I'd talk about, and usually when you send emails to people and say, this is my abstract, you have to go back and check it because you send the abstract in haste and then you have to actually talk about it. So I think I'll pretty much stick to the agenda, unique characteristics of renewables and how they integrate across the whole energy system, so I think that's fine. It'll be about wind and solar. I'm a grid guy, mainly I'm a power systems guy, but I will talk about other energy systems as well. In particular, I'll talk about this concept of the whole energy system and integrate it together. My view is, ask me questions as I go. I'm very comfortable with that. It's the best way to do it. What I would say though is, well, okay, I'm an Irishman, I suppose I have to take a little bit of a joke about myself. There's many characteristics of Irish men. One of them is drinking beer with Robert. But the other two are luck, yeah? And I've been very lucky, so I think when you say I've got charisma, I've been very lucky. I happen to be an electrical engineer in the right place at the right time. I think that's a large part of it. The other thing about it is we can talk. And we can talk and talk and talk and talk. So I'm going to ask Robert to keep me on time, so if I start to drift. So if someone asks me a question and I go off on a tangent, he's going to say, Mark, come back to the main topic, okay? So the outline, I'll say what it is, why it's important. I'll talk then mainly about variable renewable energy. I'll talk about its technical characteristics and the resource characteristics, because I think they are the two main things that you need to understand about integrating them into systems. One is the technology, the other is the resource. And I'll talk about this bigger energy systems integration issue. These are well-known slides. I'm going to use them twice just to start off. This is the so-called business as usual type of situation for the world, and this is the so-called 2DS. Robert has views on this. I'm sure he could share them with you another time. But the basic concept is that there's going to be more and more renewables in the system. The other thing is if you look between the two of them, there's more interaction between the different vectors, and I'll come back to that later. So this is a very nice slide. I think it's a good one, is it? Do you like it? Have you seen it before? So it was used by some Germans recently. So it's showing you wind and solar pushing the thermal power plant off the edge of the cliff. So I think it's a very nice diagram. But let's get to what it really means then. This is a 2011 slide from the IEA, and it's a graphic from there. The same data is true in the 2013 report, but in the 2013, the most recent reports, they don't present it like this, so that's why I use the 2011 slide. What it shows you is they're about to invest 38 trillion in the energy infrastructure of the world, and half it is in the power grid, okay? Now, the numbers I think have gone up to 42 trillion in the most recent estimates, but the simple fact of the matter is renewables are capital intensive. There's huge amounts of money to be invested, colossal amounts. Like that's even a significant number with regard to your debt. In fact, it's only half your debt, or what is it, twice your debt? Anyway, your debt and it are about the same. So the reason this is the electric future. So again, like I said, I'm lucky. I happen to be an electrical engineer, happen to be in the right country, right time. The world is electrifying. if you look, let's go to the next slide very quickly. Or sorry, I don't have that slide, it's in the rest of the slide deck. If you look at the growth in energy use, it's going up by such and such a percentage. If you look at it in terms of electricity, it's going up at a faster rate. And the reasons are, if you want to integrate renewables at scale, electricity is the way to do it. Nuclear, decarbonization, if you're going to go nuclear, it's electricity. And if you try and decarbonize transport, for example, one of the ways to do it is with electric vehicles. So there's no doubt about it that electrification of the world is happening more and more and more. And if you look at the greatest engineering achievements of the 20th century, it was electrification. And these are the National Academy of Engineering have this running sort of list of where they think the 21st century innovations are. My belief is that in the 21st century, the electrification will also win. It'll win the 20th century and the 21st century. That's my prediction. I don't think I will be here. I'm not sure. Some of the younger people here with technology may still be here by that time. So they talk about the trilemma, the so-called competitiveness, sustainability, security, supply. And if you look at this quote from the IEA World Energy Outlook in 2014, difficult task for investors to navigate policy and market uncertainties. I mean, there's a huge amount of uncertainty out there, colossal amounts of it. And if you talk to people in the industry, the number one thing they want researchers to do is to reduce the amount of uncertainty, either by technology, policy, whatever. Because they have huge investments to make. For example, if you want to do an offshore wind farm, you're not going to do one for anything less than a couple of billion. And that's a lot of money. So there's huge investments to be made. So we take the competitiveness issue. Shale gas is obviously important there, sustainability, security, supply. But I actually believe that the trilemma is wrong. I believe that consumer is actually an incredibly important part of this. This is a quote from a friend of mine, Yanis Bialik. He was in Durham University. He's now in Skaltech in Russia. He says engineers, and he put in an economist. I don't know why he did that, but he did. He lumps them with us, tend to be ignorant and arrogant about customers. And if you look at it, for example, we want to bring renewable energy to the customer. They want it, but they do not want us to build a transmission. This is really funny. Smart meters are not healthy for children and other living things. So there's a real problem with the consumer. Oh, sorry. I'll call them the consumer. The social scientists will tell me that's the wrong term. I plead ignorance. So I just call them the consumer. It's a generic term. So in fact, I believe that this is an initiative that's going on in Europe run by Linda Stegg, who's a social scientist in Groningen. So this is a platform for energy research and socioeconomic nexus, 2014. So the European Commission recognized that the consumer is fundamental to everything. If you look at the new SET plan, integrated roadmap, the consumer is central to everything. So I'm not here to talk about the consumer, obviously, because I'm an electrical engineer, but nonetheless, in everything I talk about, I think the consumer needs to be accounted for. So I think it's the trilemma plus the consumer is the issue. So just in the sort of, that's my first set of slides to sort of introduce it. It's about energy transition, electricity, money, environment, consumer, security, supply, etc. It's about all these things. I mean, electrical engineering is here. You can see it. But it's just there. It's about regulation, policy, all these good things, okay? And it's all very uncertain. Any questions? You're a very dour audience, I have to say. What? Faster. I can go faster, but then there's no questions. Faster. Are you my master? Okay. You want me to get to the meat, is it? Yes. Okay. Well, he's a man who speaks the truth. Okay, variable renewable. Okay. I hear you have a reputation for that. Variable renewable energy characteristics. So let's talk about this. So we all know about PV. I don't have to tell you about it. It's grown dramatically in the world. We know about wind. It's grown dramatically in the world. So let's talk about Ireland then, my own country. So this is the growth of wind in Ireland up to 2014. The thing about Ireland, though, if you think about it, if you take it, is that it's got the highest penetration of non-synchronous generation in a power system in the world. So let me explain what that means. So if you look at synchronous power systems in Europe, they're in color-coded here. The main one is the main European grid, which stretches from Spain up to Poland, down as far as Greece. And it used to be called the UCTE system. This is one synchronous power system. And the way to think about it is like a tandem bike. All the generators are essentially, from a mechanical analogy point of view, locked in together and all working to spin the bike. The Irish power system, the Great Britain, are all non-synchronous. They're not synchronous. They're not synchronously connected with the European grid. They're their own bicycle, their own synchronous system. And then you have the Nordic system. Denmark is an interesting place because it's actually on both. It's on the European grid and on the Nordic grid. So that's very important, because when you come from a technology point of view to integrate renewables, the amount, it's got to do with the number of renewables with respect to the size of the whole system. So you don't go and say Denmark has an awful lot of wind and therefore it's a world leader. Denmark is essentially a very small region within two very large power systems, and therefore from the point of view of integration, that's an almost irrelevant statement. You know, what is important, if you take a synchronous power system, so Northern Ireland, Northern Ireland, Great Britain, Continental Europe, these are all the synchronous power systems. These are the current, penetration rates in 2010, 2015, and 2020. And as you see, this is a European view, but if you go anywhere in the world, the Irish power system has the highest penetration of non-synchronous generation in the world, and will continue to do so for years to come. Now, I'm going to sign this release of this video, so if I say what I'm about to say might be a bit undiplomatic, we might take it out. There is one exception to this. There are small islands in the world, they're holiday islands, that have higher penetrations. But what happens when the electricity goes out? You drink the beer and eat the ice cream, because, you know, they don't have a serious power system. It's not, they're generally holiday islands. So there are some systems out there that have higher penetrations, but they generally do not have the level of reliability that we would have. We have an Intel fabrication plant. We would not have an Intel fabrication plant if the electricity went out every now and again. So it's the highest penetration of non-synchronous generation in the world. And I don't know whether I should have used this slide. I put it in this morning, and maybe I shouldn't have. I mean, to try. So how many people here are electrical power engineers? Huh?
Assuming you can follow the graph.
Yeah? Okay. So this is my analogy for electric power system. It's a mechanical analogy. If you take it as a tandem bike, if you take the blue synchronous generators, they all work together. And the analogy is that they're mechanically coupled together by these chains, okay? And therefore, you know, if somebody on the bicycle, if one of those people on the bicycle, you know, rams or does something on the bike, everyone else feels it, okay? So they're mechanically coupled. If you put on, that's a synchronous power system. If you put on wind or solar, they are generally connected now with power electronics. And that essentially decouples them. And the way I have it drawn here is that the older technologies in wind were fixed-speed wind turbines. Essentially, they would be asynchronously connected. They wouldn't be connected by a chain. They'd be connected by a loose sort of coupling. If you go down to the more modern ones, doubly-fed induction generators and, say, PV, they're still coupled to the system asynchronously, but they do not add to the weight of this shaft, okay? So from the point of view of and what's happening is we're pushing off the synchronous generation, the blue stuff, replacing it with the green stuff. This shaft mechanically is becoming smaller and smaller and smaller. And therefore, from a kinetic energy point of view, if you do something, if you take one of the generators off, the speed of the shaft will slow down quicker because there's less kinetic energy stored in it. So it's a classic case of inertia. And this is one of the biggest problems that's facing integration of renewables. This shaft essentially is getting smaller and smaller and smaller, and frequency control is becoming much more difficult.
Is that because the whole system as a whole is not growing? Because otherwise it could be, the shaft to be getting bigger and there could be more.
Yeah, I mean, if you go to China, for example, they have huge low growth, and therefore, you know, they're putting everything on. But if you go to Europe at the moment, you find that the synchronous, you know, literally renewables are pushing synchronous generation off the bars. The shaft is essentially becoming lighter and lighter. And in our system, it's becoming lighter and lighter. And not only is it a theoretical thing, but we have data that shows that this is actually happening. And in fact, I'll go on to talk about that further. This is the so-called non-synchronous generation issue. This is what they call the inertia issue. I've got 50/60 because in Europe we run at 50 hertz, and in the US it's 60 hertz. And if you don't get it right, you black out. This is the famous picture from space of the US during the Eastern Interconnection blackout. So if you do not maintain the speed of this shaft at the correct speed, the system will black out. And just to put it in context, the amount of kinetic energy stored in the total rotating masses on most power systems, if it was the only source of energy for the system, would last for how long? So, you know, a certain amount of energy in the rotating mass, just say it was the only source of energy for the whole system, the load was consuming it, no energy was coming in. How long would it last?
5 seconds.
Yeah, 5-10 seconds type of thing. So it's not a case that this shaft has sort of got 20 minutes worth of it. It's got 5. I think 10 is probably closer, but different systems. So it's not that there's an awful lot of energy stored there. It's a tiny amount. So in other words, the maintaining and supply-demand balance is incredibly important because you do not have this huge amount of energy stored in this rotating masses. So it's pretty critical. If you look at the Italian blackout that happened 5 years or 10 years ago, they essentially had a frequency problem. It took 2 or 3 minutes for it to happen because you're not going to suck out, you're not going to cut off all the generation, etc. It's not going to be dramatic, but a few minutes. In the Irish power system, because we're so small, it's not a case when something happens that somebody has time to do something about it. 5, 10, 20 seconds is all you've got. So it happens very, very quickly if you don't maintain this. So the Irish power system has this huge penetration, and that's why the synchronous nature is so important. The mainland Europe, if you go back to it, they've got this enormous amount of kinetic energy relative to us, okay? And the penetration level of non-synchronous generation is pretty small, relatively speaking. And therefore, they don't have problems with frequency control at all. We do. Texas does, because it's a synchronous system in its own right. It's got a large amount of wind in the system. So this is the so-called inertia issue that people are starting to talk about. But we're not starting to talk about it. We actually have it right now. We actually bump up against this. So we did a study in 2010. These are the results of it. This is a journal paper we published on it. And just to explain very soon, so it's load, it's wind. The diagonals there, the sort of semi-diagonals, is SNSP, synchronous non-synchronous penetration, which is defined here. Wind plus imports over demand plus exports. These are boundaries, and the green area indicates an area that we're pretty happy the system can operate fine at. So you can see the load varies from about 3 gigawatts to 8, and the wind then is along this axis here. So we have a situation is if we had a fault below that 50% SNSP limit, there's enough kinetic energy on the system to make sure the system does not black out. If we go above the 50%, at the moment, the way the system's configured, it's in this danger area where we believe that we may not recover from the fault. Sorry, in steady state, this system is fine. There's no problems with the system at all. It's what happens if I lose a generator. If somebody falls off the tandem bike, so to speak, okay? One of the generators disappears. Then all of a sudden you've got an imbalance. The system slows down. It'll slow down so fast that you can do nothing about it if you go beyond 50%. Between 50 and 75%, we believe there's ways of getting us there, so we can get to 75%. Beyond 75%, there's a fundamental change to the power system. So just to show you that this is not theory in any way. This is early 2015. This is the Irish power system. This is SNSP. This is us curtailing wind at the 50% SNSP. So this is not a theoretical future thing. This is here and now. We curtail our wind not because we don't have the transmission, not because we don't have the flexibility, simply because if there was a fault above that value, we are unsure whether the system would ride through it. And therefore, prudent system operation is to curtail it. Now, I could go off on a tangent. There are ways to get to 50 to 75%. But if you think about it, what's actually happening is this, is that, and it's just one of those sort of quirky things. Once you go over 50%, essentially what's happening is the system is no longer a synchronous power system. At the moment, our system is essentially a synchronous power system with some asynchronous generation. If you go over to 50%, it's an asynchronous power system with some synchronous generation. Its characteristics change. And if you look at all the textbooks, and if you look at all the classic power system engineering, it's based on one principle. This system is synchronous. If you go over 50%, essentially that comes into question. And it opens up a huge area of research that needs to be done, because if you go more and more renewables, you will start coming up to 50, 60, 70, 80%.
So this in particular should not depend on the scale.
No, this doesn't, well, okay. Yeah, the answer to that question is the principle does not, the scale, so this will happen everywhere. But it's not linear. I'm not saying that if you did a study on the Eastern Interconnection in the United States, it would be the same, or the Western Interconnection in the United States, or the UK. So I got a question about that from the UK, from Great Britain. The difference between Great Britain and the UK, of course, clear. Northern Ireland is on our system, etc. But I got a question from them. It doesn't scale linearly, no. I think, but it's in that ballpark. You'd have to do the numbers. Okay, it's the public domain report is online. It's around about 70 pages. The internal report's around 300 pages. It's not in the public domain. Huge numbers of power system studies were done on the system. In other words, lots of cases were tried. Also, you got to remember, an awful lot of our wind is on the distribution network. They're not connected to the transmission network. And one of the problems we have is that if you lose a large generator, the lack of kinetic energy means that the rate of change of frequency is enormous. And we have a rate of change of relay frequencies, rock-off relays. they're there to protect distribution-connected wind if they were disconnected from the whole system. When they see the frequency change the way it does, they think they've been disconnected from the whole system. They're not. The whole system is undergoing a huge frequency change, and they trip off. And so part of our problem has to do with the way our system is configured. Part of our problem has to do with an awful lot of our wind is distribution connected. That's also true in Denmark, but it's not true in the United States. So different cases, but the fundamental principle is there. I just, sorry, before you get in, Robert, one thing I'm just about to go on here. This is an NREL study on exactly the same issue done on the Western Wind Integration Study Phase 3. It's a simulation study. Ours is not simulation. Ours is, we're really hitting it. And they're starting to find the same concept for the Western interconnection. Sorry, Robert, go on. Yeah, okay. So it'll happen everywhere, but at different levels depending on different circumstances. So it's been done, the studies they're already looking in the US. This is an article from IEEE as well. So there's actually they're starting to look at it in mainland Europe, because if things keep going the way they are, everyone will suffer from this problem. So future, greater than 70. So we think the research essentially has been done on how to get from 50 to 75%. It's published. They're starting to implement it. EirGrid intend to push this limit from 50 to 75% over the next couple of years. Because if they don't, we're trying to hit 40% on electricity from energy, around about 22% now. If they don't address this issue, what will happen is we'll be curtailing 15, 20, 30% of the energy. And that's uneconomic. So we have to get from 50 to 75%. This is, if you go to huge penetration levels though, what happens is in fact the entire system becomes an asynchronous power system. And you have to question the entire, in fact you go back to this, you know. Tesla was a brilliant man and Edison was the businessman, and Tesla did win out in the end, which is good. But maybe in hindsight, you know, why are we even using AC? You know, that's another question. But, you know, the answer to that is very simple. You know, we've an amazing amount of money invested in the AC system, and it's going to be, you're not exactly going to build, you know, a brand new system beside it. So whatever way you have to do this, you have to transition it. So the analogy I'll give you, it's like flying a 777 or a Boeing 747 across the Atlantic and changing all its engines in mid-flight. That's what it's like, because you can't turn this system off. So the transition is incredibly important. So some very good work been done by people. This is Brian Johnson from NREL. I met him there 2 days ago. They're doing some really good work on trying to get power electronic devices in a way that they can actually handle this transition. In other words, that we make more and more power electronics, but we maintain an AC system. There's a big European Commission research project just been put in by RTE and TenneT on the whole issue. So it's a really interesting question is, should we go to DC? It's going to be an asynchronous power system, but yet we're going to have to sort of make it look like a synchronous power system, because that's the way the entire system was built. So it's a really, really interesting challenge, and it's a power electronic challenge. So Ireland has the highest penetration of non-synchronous generation in the world. It's a power system dynamics. In the end of the day, the limits to renewables is actually a power system dynamics question, which is great for people like me. It is essentially a good old-fashioned electrical engineering question. We'll get to 75% SNSP soon. Going beyond that, it is a game-changing issue that is a real, you know, task of research. Very intensive research is required. And particularly people in power electronics is a good area to be in. So let's talk about the resource characteristic itself. I'm sure I don't have to show these, but I will. So this is May 2011 wind output from Ireland for 3 days. It also shows the yearly average, and it also shows the monthly average. So a couple of points about it. No surprise, wind is different on different days. It's very variable. Everybody knows that. The other things to notice, though, is that we have a diurnal pattern. If you look at the black one, it's the average. We have a diurnal pattern that's very positive towards us, and I'll show that later. It tends to be windier in Ireland during the day than at night. Now, in Texas, it's the complete opposite, and I'll show that later. So our wind resource is a very good wind resource. The May one, I'll come back to as well. May is a summer month in Ireland, right? It's windier in the winter than the summer. Why is it then that May 2011 wind was almost twice the average for the year? And the answer is, this stuff is variable across all time scales. And in fact, May 2011 was the highest wind production month of all time on record, despite the fact that on average, it was around, it should be around 60% of the black one. It was actually 100% greater than the black one, which shows you that it's variable on all time scales. And in fact, as it turns out, December 2011 beat it then, which is not unusual because December should be windier. So that's what the next one shows. So that's May 2011. We had a 47% capacity factor in a month that we usually have a capacity factor. If you look at the May previous to it, it was around about 14%, 47%. So it's variable on all time scales. And in fact, in 2010, if you look at it on a yearly basis, the capacity factors of wind were, in Ireland, we're going from around about 29 to 31, 33, 34, 35%. 2010, it dropped dramatically. It dropped by 30% from the running average. So it's variable on all time scales. And averages are irrelevant completely. Because if you're trying to design a reliable power system, adequate power system engineers, one thing they're good at extremes. That's what they do. They don't care about the average. It's irrelevant. They're worried about that one hour in the year. That's what keeps them awake. Because the normal case is easy. So forecasting is obviously an important technology. I'm not going to speak too much about it, but it's a very important technology. So it's variable and it's difficult to predict. So this is a sort of an overview slide of the whole thing about power system operations. So it's power systems 101 in one slide. Okay. So in real time, you have to supply the electricity. Okay. In this room, we have this light. There's no great storage. That rotating mass is 5 seconds worth, so there's not a great store. It's been produced and consumed at the same instant in time. In order to get to this point in time, many years before, somebody has had to plan it. They've had to build the infrastructure, build the transmission lines, etc. The various people are involved. There are regulators, there's investors, there's system operators, there's bankers. All these people are involved. They have to finance this. They have to do all the regulations, etc. The unit commitment problem, weeks or hours in advance, you have to decide what units to turn on and off. You decide maintenance schedules. Coming closer to real time, you have to decide the economic dispatch, and then you operate the system. And if you don't get it all right, you black out, and you have to balance the system. The system has to be almost in perfect balance at every instant in time because the amount of kinetic energy stored is so small. And at all stages, there's forecasting. They forecast economic growth. They get that badly wrong, as we know. They have to forecast everything. But look at it. Who would have predicted 2010? Who would have predicted May? So it becomes a very dynamic problem in terms of running this system. So from a planning, operations, real-time operations, it's variable and it's uncertain across all time scales. And therefore, it's a very interesting and challenging area. So let's go to some of the more. So this is a slide. Just to point out, a lot of my slides are from my friends and colleagues. Not all of them have the source at the bottom. I was going through them this morning, so some of them have, but I get them from various friends and neighbors and relations, essentially. So if you look at this is a study done by NREL. This is Michael Milligan. And this is showing you that if you put more and more wind, so this is now turning to the sort of the so-called flexibility issue, okay? So if you put more and more wind and solar on the system, it's a zero marginal cost resource. You should take it if you can, okay, because it's the economic right thing to do. But in order to do that, you end up in a situation whereby the system, in order to maintain balance, is going to have to ramp more dramatically, and it's going to have to, some of the generation is going to have to go down lower. So steeper ramps and lower turn down. This applies to both wind and solar, although this graph, I think, is for, yeah, it doesn't actually say, oh yeah, it does, yeah. So this is for wind, but with solar, it's somewhat similar.
Keep it back on that.
Sure.
Maybe not the only one who having trouble understanding the load and net load. You're simply subtracting the gray from the red to get the purple.
Yeah, the assumption is that the wind is zero marginal cost, so you will try and take it. So essentially what you're doing is the system operator is now looking at a case whereby every day they would have a load profile that they would meet. Now they're having a net load profile that includes wind and solar.
Like at the right, you can't have nothing else can be running.
Over here? Yeah. So, and this is part of the problem. The system operators now, every day is not the same. Every day is becoming different. And that's part of the issue. And in fact, you know, a lot of this has to do with, like, back to the bicycle issue. It's like riding a bicycle. You just have to get used to it. This is not, don't get me wrong, this is not difficult, actually. It's just, you know, you just have to accept that you're not going to do the same thing every day.
So is this data or is this a simulation?
This is simulation data, yeah, from NREL. But it's a very nice slide. I could show you real data if you want. We have real data as well.
Sobering.
But it's a very nice graph, and there's lots of these out there. So if you look at flexibility, so flexibility, you know, this is the most topical word in this area at the moment is flexibility. I'm probably responsible for it in some ways, me and some of my colleagues in this area. I don't know where exactly we started talking about it, but everyone now talks about flexibility in this area. So if you look at flexibility, though, you know, and this is a graph. It actually came from ViewVig. It came from Charlie Smith and NREL. I'm not sure exactly, but both of them were involved. And they did this sort of. It was a graphic to try and show people, look, you need flexibility. Flexibility costs money, and there's some sort of, you know, attempt to sort of rank them in terms of cost. Okay. Now, I'm not here to defend the exact order, and I don't want to get into a sort of argument about it. But the simple fact of the matter is, if you go down to the bottom left, so this is demand-side flexibility, supply-side flexibility. So, and markets could be in either. I mean, you find that in this whole area in terms of flexibility, the single best way of getting flexibility initially is institutional issues. It's not physics. You find that there's rules, regulations, market structures, et cetera, that essentially inhibit the flexibility. That's generally speaking what you find. You then, if you want to make, you know, in our system, our flexibility comes from gas plant. We have an awful lot of combined cycle gas plants. They're very flexible, so we get that. If you have pumped hydro in the system or existing storage, it's very flexible if it's existing, okay? Curtailment is a form of flexibility. You know, sometimes the best thing to do is to throw the stuff away. It is the single best thing to do for sure. This idea that somehow you have to not curtail renewables is not sensible at all. Because in order to do it, you might have to build, what's the point of building $1 billion worth of transmission to save a kilowatt hour? It doesn't make sense. So curtailment is one of them. And you get up here, and then new electricity storage is still very expensive, and I'll speak about that later. So that's sort of ranking. So let me talk about some of them. But before I do, I mentioned this already. You find that, and this is the same data as before for Ireland, but presented in a different way, and data from ERCOT Texas. This is yearly wind and load data for Ireland, averaged over the whole year on a 24-hour basis. And you can see again that we've got this, and it's normalized to 100%. You've got this diurnal pattern for wind, and you can see our load. This is the same exercise done for ERCOT. The simple fact of the matter is, and I call it dance partners, Irish wind and Irish load are much more compatible with each other than ERCOT wind and load. ERCOT, it tends to be windier at night during the spring. Their load is heaviest in the summer during the day for air conditioning. We have a beautiful situation whereby our wind tends to be windier during the winter, during the evening peak, and it's exactly correlated with our load. The best one I've ever seen, though, is actually New South Wales wind in Australia. It's even more correlated. On average, sorry, and let's be clear, I'm sinning against myself in some ways because I said that averages are not that, but you know, in this case they do mean something. So you get a situation whereby some places from a flexibility point of view, so you can't go and compare systems. You can't say, oh, we can do it, why can't you? If we compare ourselves with ERCOT have a much more difficult issue from a flexibility point of view than we do. This is what this says. Let's look at some of the others. We look at flexibility charts. So this is from Yosoda Yo. He's a Japanese friend of mine. He did a very nice graphical sort of illustration of flexibility. So you can get flexibility physically from interconnection, hydro, combined heat and power, CCGT, pumped hydro. And we've got Denmark, Ireland, and Portugal here. And actually, they would be the countries or regions in the world with the highest penetrations of non-synchronous generation, for sure. And you can look at it. How we do it is gas, mainly, okay? We've got this big spike in CCGTs. How the Danes do it is they have a massive amount of interconnection. Denmark has around about 4.5 gigawatts of wind. It also has around about 4.5 gigawatts of synchronous. So, sorry, some would say synchronous, and a lot of it's synchronous connection. So like I said, they can, in fact, the running statement is Denmark doesn't integrate wind. Europe integrates Denmark's wind. That's what happens. And let's be clear about it. This is not sort of the Danes not doing their job. The economics dictate that that's the way it should be. And a lot of people go and the people go and say, Denmark is not reducing its CO2. And in fact, that's probably true, because what happens is that Danish wind is displacing coal in Germany, essentially. So in fact, the Danes are reducing the CO2 in Germany. But the market economics dictate that that's the right thing to do. Technically speaking, the statement that Denmark CO2 is not reducing is actually correct, because Danish thermal power plants tend to be more efficient than their German counterparts. And so what happens is they essentially, the wind is exported to Germany because the thermal power plants in Denmark are more efficient. So, but interconnection is the main way to do it. CHP, the Danes have also managed to make their combined heat and power flexible. Portugal does it in two different ways, many different ways. They've got some gas, they have some interconnection, they've got some hydro. Interesting though, their interconnection is to Spain, and Spain then is not that well interconnected to France. So this is sort of very simplistic view of life, but this is how they do it. If you wanted to, one of the things people want to do now is they want to measure flexibility. They want a number. You know, the regulators, policymakers say, 1 to 10, how flexible is my system? Now that's a nice thing to ask, but it's an extraordinarily difficult thing to answer. So we've done some work on it, as have some others. We've got 2 papers in at the moment. They are, well, what's the word? They're inaccessible to policymakers, that's for sure. We haven't got ourselves to a situation where we get a nice metric that we can give to policymakers. This is a sort of a power system engineering aspect. But you can measure flexibility, but it's extremely difficult to do.
What is IRRE?
Insufficient ramping expectation. So it's a metric of inability to ramp. IRRE. It's our own definition. And let me explain it. What it's saying is that on these results here, this is time, because the other thing about flexibility, it's time dependent. Yeah, you need to be able to ramp over how long? 15 minutes, 20 minutes, an hour, 2 hours. So you have to do it across time horizon. The different ways of operating it, no reserve. So there's different policies. You can have different operational policies which will change it. But basically what it's saying is, in this case here, that the insufficient ramping expectation, I'm not sure what the second R is, but it's basically the inability to be able to meet this ramp. That's going to happen. And as you can see it goes up and up and up. Now this is quite an inflexible system for illustration purposes, right? And you can see it goes up to 4 hours. And you find, if you look at the reason why it drops dramatically at 4 hours, because on this test system there are combined cycle gas turbines that can start in 4 hours. So that's why it drops off dramatically. Okay? But it's a very difficult thing to calculate.
Excuse me.
Yeah?
So why does it actually peak somewhere? I mean, shouldn't actually the higher points be earlier? I mean, what is going to instantaneously? No,
because at very short time horizons, you'll always have some resource that can move up. The problem is that as you try and move up more and more and more, you run out. And the reason why it peaks at 4 hours and drops off, because within 4 hours you can turn something on. I mean, in my opinion, although this is a very nice journal paper and I'm very proud of it, I actually think that my colleague in Japan, that this is probably a more useful thing to do, because it's graphical, it's simple, you know, I mean, it has its flaws too, but I think if you go to in fact, I had no questions on this slide, but if I had questions on this slide, you can imagine the policymakers. They're going to go, what is this? What do you mean by horizon? You know, what do you mean by time? What's this? So, you know, they wouldn't get it at all. So you're probably better off boiling it down to something like this. So I think Yasuda was, it's one of the simplest ideas I've ever seen, but it's very, very effective.
So you would tell the policymakers to look at the area of the polygon?
Yeah, possibly, yeah.
And say that if the area is large, they're more flexible?
Yeah, I mean, yeah. But, yeah, you see, that's dangerous. Because let's go to Portugal as one of them. The problem with Portugal is its interconnection part is tied to Spain. And Spain then, to the largest system, has a huge transmission congestion problem. So I would show it to them, but I would come with an expert who would be able to explain it. I mean, what's going on at the moment in this area is people are trying to replace experts with simple, you can't do it. You need somebody, you need the human being in the room too. But there are people who are trying to replace the experts. But this is a good illustration. I mean, essentially, Ireland does it with gas, Denmark does it with interconnection, Portugal does it with a combination. That's the message. You know, but no one system is the same. And I could also show you, I've got another slide. it's important to remember curtailment in this. Each of these has, Denmark has virtually zero curtailment. We have around 2% curtailment. Portugal has around 2% curtailment. So curtailment is an important metric to put on the chart, so to speak, right? Because if you look at other places, they have huge amounts of curtailment, which is a hidden number. Because there is one way of integrating lots of renewables, is to throw them away every now and again. That's a perfectly, and like I said, sometimes that's the economic thing to do. And I'll talk a bit more about that now in a minute. So I think this statement is, I don't know, I think Charlie Smith is the originator, rather. If you love wind or solar, you have to at least like transmission. Now, Terry Boston from PJM was at a meeting on Monday. He's the CEO of PJM. And he said, if you like wind, you must love storage. But in fact, I think he took that from Charlie Smith's statement, which is if you love wind, you have to at least like transmission. But again, it brings up the consumer issue, or the people, their citizens, whatever. They don't like us to build it. It's the single most effective means of flexibility in a power system is building transmission. Because A, it's cheap. B, it makes the geographical footprint bigger. It enables you to get flexibility from other places. It is well-known technology, and it is the way to go. Problem is, society does not want us to build it, and that's a real issue. That's where the consumer comes in. So these are slides from LBL. This is from Andrew Mills, he works with Ryan Weiser. This shows it very simply. I don't think it's anything dramatic. The bigger the footprint, it averages things out. This makes life easier, which I think is pretty obvious. You can do reserve, in order to sort of operate these systems, you have to, one of the other ways of integrating lots of renewables is to make sure you have enough reserves online. There's various ways of doing it. This is a technique that we brought up. Just to point out, on the Irish power system, effectively they have not increased our reserves at all. Okay? So I think that's, and in a lot of systems that have integrated a lot, the reserves have not actually increased an awful lot. And that's a fact. But it all has to do with this, let me go into this. It all has to do with how you schedule the system. Reserves are there for when, reserve is power plant that are essentially ready to do something if something happens, okay? That's a simple explanation of it. But that actually depends on how you actually operate the system. So if you schedule the system every 5 minutes, that means that you only need reserves for 5 minutes in between the scheduling periods. So it all has to do with how you operate the system. So all these things interact with each other. So you can schedule it to integrate, to get rid of variability and uncertainty. You can do stochastic unit commitment and forecasting to do it, and you can do reserves. And all these things here are all not physical, every single one of them. They're being smart, operating smart, etc., and they're all not physical. I was talking previously about physical. Here it's transmission. Previously to that, it's about, about interconnection, etc. So I've now moved on to the non-physical things, which are things like faster markets, calculate your reserves correctly, stochastic unit commitment, etc., etc., etc. So curtailment is healthy. So I said this before, a certain amount of curtailment is a good thing. In my opinion, if you come across a system that's got a large penetration of renewables that has no curtailment, invariably I'd say you've probably overinvested in something. Okay? If you come across a system that has 20% curtailment, you've probably not invested enough in certain things. So there's a sweet spot. Exactly where that is, I do not know. My own guess is 3, 4, 5% is the number. Anything above 5% looks a little high. And if you take the case of Texas, so curtailment was up to 17% in 2009. It's now, as far as I know, down around 2%. And the reason is they went off and built this competitive, it was a transmission problem. They went and built an enormous amount of transmission. And that was the right thing to do. And now there's this enormous amount of transmission. People are coming into the panhandle in Texas building enormous amounts of wind. And if you look at the costs of the wind, it's actually cheaper than gas from what I can see. So curtailment is a good thing. How much, I do not know. So let's go to 100%. Let's take ourselves into the sort of the realms of, if we went to 100%. This is wind average on a monthly basis in Ireland for 2010 and load. And the wind is scaled up so the area in the curve is the same. In other words, the same amount of energy. I've got, it's a very simplistic thing. And what you notice is that in Ireland, and this is the resolution here is a month, I realize that. We could go to days and hours and weeks. If you look at this, essentially what you're saying on a monthly basis, we have too much energy in the winter and not enough in the summer. Okay? So some people say use demand-side management. Well, I don't think you're going to be able to charge up your car for the winter and drive it all summer. So that's just not going to work. If you look at the amount of, if someone says storage, if you look at the area, that's the missing area and all the rest of it, and say how much energy you would have to store. We have one pumped hydro station. It's 300 megawatts. It lasts for 6 hours, 5 or 6 hours. We'd need 5,000 of them. Okay? So that's not going to work either. So this is a thought experiment. The only way you could do it is, well, you could overbuild the wind. That's one of the things to do. Another way to do it is that maybe we should just, live our lives according to how the availability is. So, for example, in this case here, large energy-intensive industries should work during the winter months, but shouldn't during the summer, for example. Or, he's shaking his head, or you have a manufacturing facility that makes certain products that are energy-intensive during certain periods of time, and other periods of time make less energy-intensive products. I think that's the way that it'll go. That's my own opinion. And again, this is how people live their lives. This is back to the consumer. It's outside my expertise level.
It's striking that PV has the right supplementary
Yeah.
characteristics.
Yeah, no, I know that. I have slides on that too, but I have to limit the number of slides. If you put PV into this as well, you get complementarity. But still, you still end up with big gaps. But you're right. Yeah, so you end up, so PV and wind. So let's talk about storage. So Tesla have announced a big announcement last week about storage. And, it's a great product. It's very interesting. And I'm sure people are going to buy them, or at least they seem to have sold them all already, apparently. Okay, and that's what they say. But so my analogy of storage is a brilliant technology. It is, if you ask a power system operator about storage, they'll say, love it, it's great stuff. The problem is the economics. And the analogy I'll give you, it's like I think this is a Lamborghini or Ferrari and a Ford Focus. I can go down to the store in the Ferrari and buy, a bottle of milk or whatever it is, some bread. I can also go on the Ford Focus, perfectly adequate. Storage is a very expensive solution for many of these problems. That's not required at scale at the moment. I think other things can be done. You can do institutional issues, transmission. So there's ways of getting, we operate our system up to 50%, no problems. We haven't had to do anything dramatic to do that. We will have to do fairly dramatic things as we go further. So at lowish penetration levels, and I'm talking about 15, 20%, 30%, you don't need it. There's other ways of doing it. Storage is potentially a very expensive solution. If storage costs come down dramatically, then fine. But at the moment, and if you look at the numbers, they're still very, very expensive. So, storage has competitors, right? And I think, unfortunately, in this case for Mr. Musk and Tesla, they're the child there. The big guys are the other things at the moment, so they're not going to be able to compete. But if they bring its cost down, absolutely. But the amount by which they have to bring its cost down, the numbers. Now, there are niches, there are islands, and there is all sorts of places where storage does make sense, but they're pretty small niches in the market. The numbers that I've seen, they'll have to divide the capital cost of storage by around about 3, approximately, before it'll become viable at a large scale. Now that's, it could be 2, it could be 4, but it's not 10%, right? It's of the order of 3, divide by 3.
Mark?
Yeah?
But also in addition, we did simulations where the cost of storage was 0, and our models still refused to use storage because of the inverter losses. So
Yeah.
I'd much rather ramp up and down gas turbines.
Oh, yeah.
Batteries for free, and I still won't use
Yeah,
them.
yeah. No, look,
And grid load.
when I was doing these slides, they're very broad. There's all these issues. I have other slides that could say that. The other problem with storage is round trip efficiency, essentially. You put energy in, you don't get it all back.
Solve the inverter problem.
Yeah,
Or get rid of AC.
yeah. There's all sorts of problems with them. The problem with storage is that if you think about it, it's first of all, it's additional capital expense. It has losses associated with it. Okay, and if you try and beat both of those, it's very difficult. So I have to spend even more capital investment to make the system work, and I lose energy. So you're right, most of the numbers don't work. For things like ancillary services and things like that, like I say, they do have applications, there are places where they work, but it's not the silver bullet, and it's certainly speaking, the problem I would have is that we'll end up with an extraordinarily expensive solution. We'll end up with a Ferrari, whereas a Ford Focus would have done. And this is one of the problems with storage. But if Tesla do what they claim they're going to do, and if they do bring down the cost of these batteries down and divide them by 3, then you're in a different place completely. You don't believe that? Yeah.
Grid level, give me batteries for free, and I still won't use them.
Yeah.
Unless I'm doing something wrong with how I'm modeling gas turbines.
Well, how much renewables do you have in the system?
Well, we've been going up to, 20, 30, 40%.
Ah, sorry, okay. Sorry, okay. Well, let me put it this way. And again,
We're already at 100%.
Okay, sorry, I should have said the following. You're going to have 60, 50, 60, 70% renewables before they make sense. I should have said that. And again, I have more slides about it. We did numbers on this before. We show that for pump storage in the Irish power system, you have to reach over 50%. Remember, pump storage is much cheaper than batteries. And second of all, we don't have another pump storage site that we could even find. So I'm talking about a case where you go way up.
You're talking about periods where the renewables actually exceed the load.
Yes.
Yeah,
Yes. This will make sense. Divide by 3 and go to huge penetration levels, and then they make sense. So run your numbers again at 60%. And I think they'll probably get in the money.
I'll send you a paper. We agree. We
Yeah,
agree.
good. Well, actually, one other thing to say, in some of the work that we've done in storage, the CO2 rises with storage, and the reason is very simple. In our case, it goes as follows. So huge penetration of renewables. I think we went up to 90%. And we did the numbers on it. And what you find is that it depends on what your interconnect is connected to. What you find is that coal in the UK, you've got interconnection, economics rules. What actually happens is that in the study we did, and it's got to do with costs a few years ago, what happened was that the storage was being used to import coal electricity from the UK at night, displacing the gas during the day. So in fact, our CO2 went up as well. So, and this is the problem with an integrated system, it's economics, interconnection, you push one thing in, be careful what happens, okay? You have to study it carefully. So there is a case actually that storage will increase CO2, not reduce it.
Yeah, but that's a policy issue.
Yep. I'm going to talk about policy as well. So this brings me on to this. So this is some work that I did with Tsinghua University in China. And it's about they have a terrible problem with curtailment. Like curtailment rates in some parts of China are up to 20%. And the reasons are, it's a sort of an institutional issue. It's also a lack of interconnection, which is a transmission issue. It's also got to do with combined heat and power. They have an awful lot of their generation in CHP. They have these very large, essentially apartment complexes, right? And they've got a 400 megawatt generator essentially, and its main purpose is heat. Electricity is a byproduct, right? But the problem is they're very inflexible, and these show you the characteristics of the heat and electricity characteristics. And basically what happens is during the winter, it's minus 30 outside. You're going to keep the heat on. You can't turn off the heat, or you can't turn off the electricity because you have to turn off the heat. And you end up in a situation where you curtail wind. So you're curtailing wind because people have to, now you can't turn off the heat because people will die. So essentially what's happening is the inflexibility in CHP.
Mark,
and this brings...
What is shaded and what is dark shaded and what is light shaded?
There are three different technologies, with the electric boiler, with heat storage, and with both together. Yeah. And the shaded areas are showing the difference between the original and when you implement this technology.
Access and not.
You're changing the characteristics. This is a relationship between heat and electricity. And basically it's just trying to show you the shading is showing that you can change the characteristics. If you change the characteristics, you can implement. Look, again, if you want me to, this came out of a slide deck that's got 10 slides before and 10 slides after. Yeah. I'll send you the paper. Actually, sorry, this paper is actually published, actually. I should have taken that out. But anyway, it brings up the whole issue that if you want to integrate large amounts of renewables, that interactions between, for example, the heat or cooling system and electricity is important. Very important. So, if you just take it, so variable renewables, certain across all time scales, and supply-demand balance is critical. So flexibility, so some things, it's very difficult to quantify. Transmission is critical. Curtailment is healthy, some curtailment. The correlation with the, between the wind or solar and the load is very important. And as pointed out by Robert, if you put solar in there, you get different results as well. Flexibility is not just physical. An awful lot of it's institutional about markets, etc. Demand-side flexibility, it can provide ancillary services, but ultimately may impact how we organize society. Now that's me as an engineer being very speculative, and it's not an engineering conclusion, I can assure you. Storage is still expensive and it has lots of competition. And I think the sources of flexibility can be actually in other parts of the energy system. So you can use the flexibility in the heat system, et cetera, et cetera, et cetera. So the last part of the talk then, energy systems integration. So I'll go back to this. If you look at this, and if you look at this, you find that in fact there's more crossover between them. So for example, there's renewables. What you're finding is that some of the renewables is going into electricity and then is ultimately going into transport. So it's trying to illustrate that the integration of the whole system is, in order to decarbonize it, this is what is a very good thing to do. So for example, maybe you should, if you decarbonize the electricity system enough, electric heating makes sense, okay? So it's all going towards a much more integrated system. And this is this concept of energy systems integration. So this is an NREL slide. So NREL have built their energy systems integration facility out in Colorado. And the whole concept is based on the fact that electricity, thermal fuels, data across all scales are becoming more interconnected. And I think that is true, and I think most people accept that. So let me give you another angle on it, though, water. So I think water is also included in it. If you think about water, water is a huge, I know in our system, 11% of electricity is used in water to pump it, et cetera, et cetera, et cetera. So it's a huge user of electricity. If you think about thermal power plant or nuclear power plant, they need water to cool. So this water energy nexus is very, very important. So it's not just about integration of the energy system, but it's also with other systems as well. And this is work done by EDF, and these are various sort of papers, et cetera. If you look at Denmark, I think Denmark is probably the leader in the world in this area because they have an integrated electricity and heating system in Copenhagen. They operate them together, they co-optimize them. They are putting in an awful lot of CHP, they're making it flexible, et cetera. And the plans in Denmark have plans to make themselves 100% renewable by 2050. Now, you ask themselves the question, are you going to disconnect yourself from the rest of the system? And probably not. But if you look at it, they have the international gas infrastructure, the international power infrastructure, and they're thinking about things like, electrolysis, fuels, et cetera. Now, these are very long-term research goals because if you look at electrolysis, converting electricity into a synthetic fuel, it's not exactly economic at the moment. It's far from it. And then reconverting it back into electricity is definitely not economic. So there's some interesting questions that have to be done there. Just on the policy, issue, policies, they have to be integrated too. This is just one example. You have a situation, this here in Bloomberg, windmills overload East European's grid. And again, I have more slides on this if you wanted to see them. I mean, essentially what's happening in Europe is that you have an awful lot of wind and solar in Germany. For policy reasons, the Germans do not have locational marginal pricing. They do not have price signals, essentially, that would tell the wind and solar to turn off. And what basically happens is that they get these unexpected loop flows through the Polish grid. They used to go through the Belgian grid, but the chairman, who's a man called Ronnie Belmans, who's a professor in KU Leuven, he put in a lot of phase-shifting transformers, like at 100 million apiece. There is technology to stop loop flows, but it's very expensive. So all that happened is loop flows now go through Poland. So it's a classic case of politicians wanting renewables, but not accepting some of the consequences, which is that every now and again you have to turn them off. And not accepting the consequences that the best way to do it is to have locational marginal pricing. So there's all these, politicians. I have a version of this slide that shows a person with their head in the sand. Politicians, they want something, but they don't want all the consequences. One of the reasons why this is still a problem, now it's getting better, they're starting to address it. But one of the reasons is that if you think about it, if I said that Germany has invested a huge amount of renewables, the consumer again is paying, customer electricity prices in Germany are enormous. I don't know what they are, but I don't know how much you pay here, 10 cents?
18.
18 cents, yeah. In Germany, I assure you, the consumer is probably paying twice that, approximately, okay? Can you imagine telling the consumer that they are subsidizing this wind and solar and every now and again you have to curtail it? That's not a message that it's easy to sell politically, but sell it they have to. So to just end, so this is this International Institute for Energy System Integration, so NREL, PNNL, EPRI, ourselves, DTU and KU Leuven have sort of established this as an organization. It's just an organization to promote this area of the whole integrated energy system together. It runs events and runs workshops, etc. We've been in existence for about a year. So recently we had a workshop in London, but you know, we had a group of people together to look at what the key research questions it is, and this is online if you want to see it. We are running a PhD, 1 week course for PhD students in the area in Colorado in August, and that's available for any PhD students who want to go to it. So it's more about the whole integrated energy system than ever before. An energy system, energy system integration can, it can reduce uncertainty, because if you put the whole system together, there's multiple options. So for example, hybrid heating systems, you could heat yourself in electricity or gas. That reduces a certain amount of uncertainty. Now there's a cost associated with that. So it is definitely a way of making the system much more resilient, etc. But the customers are central to the entire thing, or the consumers are central to the entire thing. So my overall conclusions then are, variable renewables, they're uncertain at all time scales. You can integrate a lot of renewables. It's just good old-fashioned engineering. There's no rocket science to this stuff at all. You can get to fairly high penetration levels without, you just have to do things well. But if you go higher, then integrating the entire energy system together is probably the way forward. In the end, though, it becomes a power system dynamics issue in terms of power electronics if we go to very, very high penetration levels. And that's a really, really, really difficult problem. Like I said, change the engines on a Boeing 747 as it flies across the Atlantic. So it's a very, very big challenge. But the consumer is key, and I have no idea what it means, do you? That's it, I'm finished. There you go, my Yes. Please wait for the microphone. You're a very conservative audience.
Thank you for the great talk. I have a question about using long-distance transmission line to integrate renewables. I ask this question because China is now proposing to build ultra-high voltage transmission lines to transport large amounts of renewable power from the Western China to Eastern China. Yeah. So I'm wondering if you could comment on the advantages and also some problems of using this long-distance transmission line for renewable integration purpose.
Yeah, okay. So, yeah, I do spend a bit of time in China, so I know something about what you're saying. So China has an amazing resource of renewables in the interior, and most of its load is on the coast, okay? So I don't think they're even thinking about it. They are building some of these already, so it's not a plan, they're building them. They're building lots of them, and they're 8 gigawatts each. So this is, the entire Irish power system's installed capacity is 10. The Chinese are transporting that across single lines. Well, not single lines, but single transmission corridors, okay? So you want to know what the advantages are? Yeah. It's an incredibly cost-effective and efficient way to do it. And if you look at studies done in the US by MISO, by a guy called Dale Osborne, if you just Google him, you'll find it. So he's in MISO. And he's done some really great work to show that in the US, the way to do it is to build huge amounts of HVDC from the Great Plains to the cities, right? And it's cost-effective in an extraordinary way, and it improves everything. Now, you have to do it at scale. You can't half do this. To get its benefits, you have to do this huge project. China can do huge projects. Can the US? And the answer is probably not. The main disadvantage of them, actually from an engineering point of view, there's no disadvantage to them. They're a great idea and they should be done. From a technical point of view, there are some very interesting, sort of very detailed engineering questions, but they can all be overcome. So there's no major problems with them at all. The major problem with doing them in the West is that they will go through other states, but they don't have any connection to them at all. And therefore, they're saying, you've got the transmission across my state, but I'm not getting any of it. The problem with HVDC is the following. AC, it's easy to connect to it. So if you have an AC transmission line, 100,000 euros, and you can connect to it, a transformer. If you want to connect to a HVDC, say one of these large ones, 100 million. Because it's DC, so you have to get a big power electronic converter, and they're roughly 100 million. So every time you connect into them, it's extraordinarily expensive. So they're really made for point-to-point, large amounts of energy over long distances. Connecting into it along the way, not economic, because every time you connect to it, it's 100 million. So that's the disadvantage. They're going to go across your land, and you're not going to get any use of it. But they're a great idea, and I think the Chinese should be encouraged to build more of them. But that's the electrical engineer saying it, and there's, you know, that may not be what society wants.
Get a couple more questions.
Great. So I have the question, and that's for the.
Did I meet you last night?
I think I did. Yes. For the speculative part, right, about when you're not an engineer, and that is if you think that the industry, right, can shift their manufacturing processes, et cetera, to sort of help match the load profile, then what's the difference? Would you envision it being more extreme to, I think Warren alluded to it, to having at the consumer level the grid go away and people buy the Tesla battery wall and they install it in their house? Because I just did the calculation for my house, and for the cost of basically building a new living room, I could buy a battery wall and PV and go off the grid, right?
Sure.
But it's whether I want a living room or I want a battery wall and PV.
Very nice talk. I enjoyed that very much. I have a question about compressed air energy storage to back up wind. Now, at the present time, and for the foreseeable future, compressed air energy storage for backing up wind won't make sense in the United States because gas prices are just so low. But European gas prices, and I presume that's true for Ireland as well, are far higher than they are in the United States. And one thing about compressed air energy storage is you have much more flexibility in siting than you do with pumped storage. And so I wonder if you could give, and big advantage is the heat rate for compressed air energy storage is far less than it is for combined cycle power plants. And I wonder if you can give me your thoughts as to what you think about the opportunities for compressed air energy storage backup, not just in Ireland, but Europe in general. And in particular, in Spain, they have a lot of salt domes, I think, which we don't have salt dome opportunities in windy areas in the United States. So if we want to do compressed air energy storage to back up wind, you have to do it with aquifer storage of air, because that's aquifers are available in the windy areas of the United States.
So can you handle both questions?
Yeah, no problems. So the question about going off grid, I mean, I didn't mention it, and just go back in time. The reason why we built this enormous transmission system and this enormous power grid was A, economics, B, economics, and C, economics, right? That was it. It was economically the right thing to do. And I include reliability into that because reliability is money. You know, so this idea that somehow we'll all get off the grid, it's perfectly possible to do it. If you want to integrate renewables, one of the things to do is make the problem bigger. What is it? Eisenhower said, you know, if you want to solve a problem, make it bigger and the solution emerges. I think that's what Eisenhower said. The same is true here. If you want to integrate large amounts of renewables, you have to make the big problem bigger. If you look at the economics of what you just said, I know that, let's say, on an individual basis, in terms of your bill at the moment, etc., it might make sense, actually. No, it doesn't. Right, so the economics don't make sense. But there are places in Germany where it makes sense, and the reason is because the individual consumer is subsidizing industry. So by going off grid, you're avoiding a tax, essentially. So there's all sorts of perversions in the market that make this look somewhat reasonable. In general, on average, it does not make any economic sense, and it doesn't make reliability sense. And that's unfortunately, a lot of people don't agree with that, and they think, oh no, we'll all go off the grid, etc. Well, go off the grid. But remember, you're going to be disconnected from that grid. You can't have it at any time. The other thing is that pricing mechanisms are such that on grid, sometimes people have pricing mechanisms where you pay for the infrastructure through a volume charge. In other words, you buy a kilowatt hour, and part of it is the infrastructure cost. If you want, you know, and one of the things, the spiral of debt, they call it. So down in southwest United States, an awful lot of utilities are worried about the fact that people are putting in PV, the volume of electricity they're selling is reducing, and therefore what's happening is the infrastructure costs are not being paid for. So what's going to happen is the regulators are going to have to go in and change the pricing model, which is, look, you want the grid every now and again, there's a fixed charge for it. So one of the things that's happening is that one of the reasons it looks attractive is because of policies and incentives that are all wrong. The simple fact of the matter is going off the grid does not make economic or reliability sense. Now that's spoken by a transmission power system type person. I'm sure there's another view, but I can assure you I'm right. So case, so yeah, I mean, I don't know, I know the technology reasonably well. There are actually quite a few sites in the United States, I think in Montana and places like that. There are some sites in the United States. First of all, just this idea of putting storage right beside the wind doesn't make sense, because the economics again show you if you are going to put storage, you should put it at a central location, so to speak, because then it has more opportunity to help you. So locating it local to the wind or whatever is not the economics of that are far worse than just putting it somewhere else. So the second thing is, I think a case in our system actually, we have a case project potential. And it's not as good as pumped storage, I would say, but we don't have any more sites. And it's definitely better than batteries. Whether it'll make economic sense anytime soon, I'm not sure. But I think it's better than batteries at the moment, and it's not as good as pumped hydro. But do not put it at a location beside wind. That's not an effective thing to do.
I'm going to take the last question and ask you how to think about a wire that goes under the Irish Sea that connects Ireland to the European grid. Is it something people want to do?
Well,
Never do?
We're connected to Great Britain by 2, and we're currently considering one going to France.
Well, why are you and I separate?
Because it's DC. And the reason it's DC is because, so it's not synchronous. It's asynchronous. It's AC system, converter back-to-back, DC system, converter back-to-back. So from a kinetic energy point of view, we're not synchronous connected.
Having an AC link between you
There would be, but the distance is too long, because AC, underground AC is very difficult to do any greater than 30 kilometers. It's a technical issue. It's got to do a compensation. But we are considering HVDC to France at the moment.
Okay, let's thank our speaker very much.